This is part 6 of the series Limits, and in this part we're going to continue our ideas of continuity with the idea of one-sided limits. Now, a one-sided limit is simply a value a function approaches as the x value approaches some target value either from the left or specifically from the right. And the way we would write a left-handed limit or a limit from the left is we would say the limit as x approaches c, and you notice this little minus sign up here as an exponent. So the limit as x approaches c from the left of f of x equals L. And here a right-handed limit or a limit from the right is the limit as x approaches c with a plus sign up here. So this is read the limit as x approaches c from the right. So this plus sign is interpreted as from the right. The minus sign is interpreted as from the left. So that's the difference between them. Let's go ahead and look at a couple of examples of left-handed and right-handed limits, one-sided limits. In this first example, what we want to do is we want to focus on the behavior of this function as x approaches -2 from the right. This plus sign is intended to indicate we're interested in its behavior from the right-hand side. So think of this function, and if you recognize this, this is the upper lobe of a circle. So I'm going to go ahead and sketch that function up here. Give it a real rough sketch. So it looks something like that. The radius is going to be 2 here. And this is what we're looking at. So we're looking at -2. What happens to the function as we approach -2 from the right? So coming from here to here. Well, if we look inside here, this x value is always going to be greater than -2. And so this limit, we could evaluate this directly, because if we plugged in a -2 into here, we would have 0. So the limit as x approaches -2 from the right is equal to 0. Now notice, had we said the limit as x approaches -2 of this function, we would have had to have said that this does not exist. And the reason is because since we're in this case, we wouldn't be doing a one-sided limit, and this function is not defined to the left of -2, we couldn't evaluate this left side. But because we're only concerned about what's happening to the right side of this function as it approaches -2 from the right, we can take the one-sided limit. That's one of the confusing distinctions about one-sided limits and just limits in general. So the limit as x approaches -2 of this function does not exist, but the limit as x approaches -2 from the right does exist, and it's equal to 0. Just as if we approached 2 from the left, we could evaluate that limit as well. And of course that limit would also be 0. Let's take a look at this. This is the greatest integer function here. And this is a stepwise function, which looks really bizarre. So what it does is it returns the largest integer that's less than or equal to any x value. So if you have any x value in this region, it's going to slide all the way down to there. So if it's 0.5, it slides down to 0. It's almost like a rounding down type effect. If it's 1, it pops up to the next level. If it's 1.4, it slides down to 1. If it's 1.8, it slides down to 1. If it's 2, it jumps up to the next level, and so on. So you can see this function is clearly discontinuous at each integer value, but it's continuous between integer values. So we want to talk about what's the limit of this greatest integer function as x approaches 0 from the left and from the right. So the first one, we're going to do the limit as x approaches 0 from the left of the greatest integer function. And then we're going to do the same thing from the right. So the limit as x approaches 0. This is the right-hand limit. All right, now let's take a look at what's happening. From the left, if we approach 0 from the left, we're coming all the way over here. As we get closer and closer, whenever we hit negative 0.5, we're sliding down to negative 1. 0.1, we're sliding, negative 0.1, we're sliding down to negative 1. So from the left, the limit is negative 1. It's always going to be negative 1 until we actually hit 0. At 0, it goes up to 0. So the limit from the left is going to be negative 1. And from the right, if we're coming at it from this side, when we have 0.5, again, it rounds down, so it slides down to 0. 0.8 slides down to 0. As we get closer and closer to 0, 0.1 slides down to 0. So the limit of this greatest integer function as x approaches 0 from the right is 0. And you can see this behavior is different from the left and the right. So the limit of this function at x equals 0, if we were to say the limit as x approaches 0 of the greatest integer function, does not exist. The limit doesn't exist because the behavior is different from the left and from the right. All right, let's continue on, and let's talk about the existence of limits. Now that we have this idea of one-sided limits, we can come up with a formal definition for existence of a limit. So let f be a function, let c and l be real numbers. The limit of some function f of x as x approaches some c value is L if and only if the limit as x approaches c from the left is equal to the limit as x approaches c from the right, which is equal to L. So the left hand and right hand limits must be the same value in order for the limit to exist. And as we saw in the last piecewise function, the greatest integer function, the limit from the left was negative 1, the limit from the right was 0, and so this condition was not true. That's why the limit did not exist. So this gives us a formal description of when limits can exist and when they can't. Now we're going to extend this idea to continuity on a closed interval. Now continuity on a closed interval says a function is continuous on a closed interval AB if it's continuous on the open interval and if the limit at the left endpoint from the right is f of the left endpoint and the limit of the right endpoint from the left is equal to the right endpoint. Lots of lefts and rights, and it can be confusing. So let's bring up an example just to show you what this is talking about. Here again we have the upper lobe of a circle. So let me go ahead and draw that, sketch it really quick. So what we have is something that looks like this, and this is negative 1 and this is positive 1. So what this is saying, if this is A and this is B, it's saying if this function is continuous on the open interval AB, on the open interval AB, which we can see that it is, it's continuous on this open interval, and if the limit at the left endpoint from the right, going this way from the right hand side, approaching negative 1, if that value equals f of negative 1, then this limit exists. And if the limit from the left at the right endpoint, so the limit from the left at the right endpoint B is f of B. So f of 1 here is 0, and that is the limit. And f of negative 1 is 0, and that's the limit. So based on the definition of continuity on a closed interval, we can say that this function, square root of 1 minus x squared, is continuous on the closed interval AB because of all those conditions being met. Now we're going to move forward with this idea of continuity on a closed interval, and we're going to look at a very important theorem. This theorem is called the intermediate value theorem, and it says if function f is continuous on a closed interval ab, and if f of a doesn't equal f of b, and k is any number between f of a and f of b, then there is at least one number c in the closed interval AB such that f of c equals k. As usual, a lot of complicated language, but it's relatively straightforward when we analyze it. This theorem is also known as the Cornstalk theorem, and what it says is if on a closed interval from a to b, if a function takes on all the values between f of a and f of b, and f of a doesn't equal f of b, then there has to be at least one number c between a and b such that f of c is equal to that value k, and k is between f of a and f of b. And the reason it's sometimes called the Cornstalk theorem is, let's say that you're growing a stalk of corn, and at one point in time the corn stalk is 3 inches high, and at a later point in time the corn stalk is 12 inches high. There had to have been a point in that interval where the corn stalk was 6 inches high. So that's what it's saying. If the function takes on all values between f of a and f of b, regardless of whether it's going big to small or small to big, in this case we're going big to small, so the Cornstalk idea doesn't really look very good, but the idea is the same. If the function takes on all values between f of a and f of b, then there has to be one number in here, at least one number, that f of c equals k, where k is between f of a and f of b. In this case, in this example, that there are 3 values of c. One here, and one here. Now, keep in mind, this theorem doesn't say anything about how to find this c value. This is what's known as an existence theorem. It tells you that the c must exist, but it doesn't tell us how to find it. But it's a very important theorem that helps prove other theorems and is used to gain insight into the behavior of functions. So let's look at an example here. Now we want to use the intermediate value theorem to show that this polynomial has a 0 on 0 to 1. Now the first thing we need to do is determine if the intermediate value theorem applies. Well, the first idea is that the function has to be continuous on the closed interval. This is a polynomial, and all polynomials are continuous on their domain, so yes, this is continuous on that domain. The issue also has to be that f of a can't equal f of b. F of a is 0 plus 0 minus 1, so f of a is -1. F of b is 1 plus 1 minus 1, which is 1. So f of a doesn't equal f of b. So yes, because it's continuous on the closed interval, and f of a doesn't equal f of b, then we know that there must be some number c on this interval between 0 and 1 where f of c equals 0, because the 0 of the function has to be 0, because f of c has to equal 0, and this is our k value, and that k value is between -1 and 1. It has to be 0. So that's how we use the intermediate value theorem to verify that certain conditions must exist. All right. Well, now we're going to enter into a new use for limits, and that is infinite limits, talking about infinite limits. And we're going to do that in the next part. So I will talk to you in the next part.